Okay, in this video we're going to look at confidence intervals, and in this order I'm going to first of all look at what they are, what are they, then I'm going to answer the question how do we find them, show you the formula and how it works, and then lastly I'm going to look at why the formula works, where it comes from. So to start with, let's have a look at what confidence intervals are. And up until now we've been talking about taking samples from a population and using that sample to predict the population, the mean of the population. So up until now, we've been in a position where we're making a statement like this. I predict that the mean of the population is, and then I'd give the value of my sample mean. The problem with this is that I don't know how accurate that estimate is likely to be. And so to get past this, we move towards a situation where instead of making a statement like that, I move to a statement like this, where I say, I am 95% confident that the population mean is between this value and this value. And the level of confidence can change, but the key thing is that I'm reporting a range of values along with an associated confidence of how accurate that is. And it's these values here, the lower and the upper values, that are called the confidence interval for the mean. That's what we're going to look at, how we calculate these confidence intervals. Okay, moving on to the how to calculate a confidence interval. Look at an example, or look at the formula first of all, sorry. So the confidence interval is given by this formula. So the sample mean plus or minus z times sigma on root n, where x bar, that's the mean of the sample that we're going to take. Sigma is the population standard deviation. N is the size of the sample. So you'll recognize this sigma on root n as the standard error that we talked about in previous lessons. And this value of z is defined by the required level of confidence that you need, whether it's a 95% confidence interval, 99%, so on. And I'll show you how that works. I'll look at a particular example. So I'm going to consider a population of students. I'm going to tell you that the variance of the population is 3.5. The sample of 50 gives me a sample mean of 173. And I'm going to use that information to find a 95% confidence interval for mu. So let's jot down what we know. I'm going to define my variable. X is the height. X bar then 173, sigma is root 3.5, and n is 50. The thing that I'm going to need to be careful to find is the corresponding z value. Now, for this question, I'm asked to find a 95% confidence interval. So I put 95% into the middle of a standard normal distribution. And I want to know the corresponding z value here. So of course I can use inverse normal. I have to be careful to use the area to the left, which of course is 95% plus this 2.5. So I'm going to be using 0.975, 0.1 for the inverse normal. And that tells me that my z value for this question is going to be 1.96. So armed with that information, I can now go to my formula for the confidence interval. So x bar plus or minus z sigma on root n. So x bar in this case 173 plus or minus. My z I've just worked out is 1.96. Sigma I had before is square root 3.5 and root n is root 50. I can get my calculator to work out these and I get the answer of 172.48 and 173.52. So my statement is I'm 95% confident that the population mean lies between this value and this value. So this is the confidence interval that I've been looking for. I'll show you how you can do this on your calculator. Fairly straightforward. Go menu, into the statistics menu, option 6. You can see option 6 on this is now confidence intervals. Now, I've got a Z interval. It's called a Z interval because I'm basing it upon a Z distribution, the standard normal distribution. So for number 1, if you're given the data, you can punch the data in from a list. I'm actually given the summary statistics in this question. So I'm going to go for statistics. It asks me for sigma. I've got to be careful to make sure I tell it it's the square root of 3.5. X bar, you remember, was 173. Size of my sample was 50, and my confidence level was 0.95. So I can opt for that. And the calculator will verify for me that my confidence limits were 172.48 and 173.52. So you can get the answer from your calculator. If you're doing these questions in a test or an exam, I would suggest that that is the working out that you would need to see to make sure that you're getting the marks for those particular questions. Okay, I'm going to look at another example. There's not a great deal that we can do to make these questions any more interesting. But one might be involving the width of a confidence interval. So here's a question. I've got a population X that I'm going to take a sample from in a moment. So I know that it's normally distributed with a mean mu that we're trying to estimate and a variance of 1.3 squared. I'm working with a 99% confidence interval. I need the width of that interval to be less than 2. So I want the width to be less than 2. And I want to find the smallest value of n that can be used. If you think about it, the bigger the value of n, the narrower that interval will be because you'll be more confident that you're accurate. So I want to know the smallest value of n that gets the width to be less than 2. And the way to approach these is to, of course, recognize that if these are my confidence limits, x bar minus this figure and then x bar plus this figure, then the width of that, of course, is going to be 2 lots of this amount, z times the standard error. So I know that the width of the interval is this, and then in this question, I'm then asked to find the fact that the width of this needs to be less than 2. So I can set this up. I need 2 lots of z sigma on root n to be less than 2. I can cancel the 2's off. I'm now left to solve this particular equation, which is hopefully going to be straightforward. Sigma's given, n's given. The only thing that I need to find is z. So I'm just going to come back to my sketch. I'm working on 99% confidence interval, 99% in the middle. So I'm going to be using inverse normal. I need area to the left, so it's 99 plus half of that 1% that's left. So I'm going to be using 0.99501. That tells me that the z value to use in this case is 2.576. So coming back up to my solution, I've got 2.576 times sigma, which was square root of, was 1.3. So sigma was 1.3 in this case, and root n needs to be less than 1. It's a case of solving this now, so I'm going to take the n across and flip the inequality. So I need root n is going to be bigger than 2.576 times the 1.3. Turns out to be bigger than 11.2. So I need n at least 12. So any questions where you're asked about the width of a confidence interval, then the key thing that you remember is that the width is equal to 2 lots of this figure that's involved in the confidence limits. Okay, I'm going to take a few moments to just have a think about this question and just try to put an image in your head about what it is that we're actually finding here. Now, it's important to remember in these situations that the population mean mu remains fixed and unknown. I don't know what it is. What these intervals do is they try to estimate where it is. So it might be, for example, that if I've got my value of mu, which might be represented as this value here, then the confidence interval given by a particular sample might be this particular interval here. If I take a different sample, then I might end up with this confidence interval. Another sample will give, again, a different confidence interval. And of course, there's also the chance that the confidence interval will miss the true value of the mean completely. So we have to have this idea that different samples lead us to different confidence intervals, and each of them is associated with the probability of containing the mean or not, as is in the case with this particular one here. And if you then think about that, let's take 95% confidence interval as an example. If I did 100 of them, if I worked out 100 different 95% confidence intervals, then we'd expect 5 of them to not contain the population mean at all. So it's worth just having that image as you figure out, as you calculate these things and think about what they are. So it's an interval which may or may not contain the true value of the mean, but I can tell you how confident I am that the mean is actually in that interval or not. Okay, let's move to the why. I want to have a look at why this formula is the structure that it is. And we're going to do that by starting off with the distribution of the sample mean. Now this is actually quite important. We're starting from the point that it's normally distributed mean mu variance sigma squared on n, as we've seen before. And what I'm going to do is I'm going to standardize this distribution to our favorite z is normal 0, 1, with the conversion formula z is x bar minus mu upon sigma on root n. Now that's 0. And what I'm going to be looking at, I'm going to look at the example of a 95% confidence interval. So for a 95% confidence interval, what I know from my diagram here is that the probability of z being between minus 1.96 and 1.96 is 0.95. I know that's true, so I can set this up. Minus 1.96 less than 1.96 is equal to 0.95. And what I'm going to do is that in this statement, rather than write z, I know that z is equal to this. So it's also fine for me to say probability minus 1.96 less than x bar minus mu upon sigma on root n less than 1.96 is also 0.95. Those are equivalent statements. So I'm 95% sure that this statement is true. Now what I'm going to do is just look at that statement a little bit more carefully. There are two inequalities in here, this one and this one. So let's just have a look at these in turn. So I'm going to take a look at minus 1.96 less than x bar minus mu upon sigma on root n. And I'm going to rearrange this to find mu. So I'm going to take the sigma on root n, minus 1.96 times sigma on root n is less than x bar minus mu. So that tells me that I'm going to take the mu over here and that over there. The mean is less than x bar plus 1.96 sigma on root n. Okay, so I'm happy with that statement. I'm then going to do an equivalent thing for this other part of the inequality. I'm going to have x bar minus mu upon sigma on root n is less than 1.96. I'm going to do a similar rearrangement here. So x bar minus mu is going to be less than 1.96 times sigma on root n. rearrange for mu, or mu over there, so I'm going to have x bar minus 1.96 sigma on root n is less than the mean. And so these statements together now enable me to write, instead of writing this statement here, I can now write, let's just move this up, I now can understand that this is actually the same as saying the probability of x bar minus 1.96 sigma on root n less than mu less than x bar plus 1.96 sigma on root n is equal to 0.95. And what this is, hopefully it will convince us that I'm saying the probability of the population mean being between these values is 0.95. So therefore, these are the confidence limits for a 95% confidence interval. So I can quite happily then say, well, it's x bar plus or minus 1.96 sigma on root n for a 95% confidence interval. And of course, if I wanted a different level of confidence, I would have used a different value of z, and that would show up in my result here. So that is how we get to that particular formula. Okay, thank you for bearing with me. We're almost at the end, but there are a couple of things that it's important for you to be aware of. This is key, really. Okay, this is the formula we use, but in the section where I showed you where it came from, it started from this. Now, of course, remember that x bar being normal is dependent upon either the population being normal, or if the population is not normal, I still know that this is true as long as my sample size is big enough by using the central limit theorem. So I can use this for small samples from a normal population or from large samples from a non-normal population. So that's important. I think we mentioned this with the calculator section. These intervals are based on the standard normal distribution, so they're called Z intervals. So you might say, I need to find a Z interval. The other thing to be aware of is that in the questions that we've looked at, we've assumed that sigma squared is actually known, which if you think about it, is probably quite unrealistic, because if we knew the population variance, we'd probably know the population mean, in which case, why are we bothering to estimate it at all? So this is a question that we need to address in subsequent lessons, but for the moment, just make a note that the questions you look at will give you the population variance. Here's a question for you just to think about for yourself. Can you answer that? If I ask you to calculate a 99% confidence interval or a 95% confidence interval, which would you expect to be wider and why? Could you argue it from the perspective of the algebra in order to get it? Could you argue it from the context of the question? So that's a good question for you to think about as you work your way through these questions on confidence intervals.